I thought this was funny with Tony Stark. It's not related to what we're doing today, but it was pretty funny. That's right. Yeah. Oh, sorry, I didn't do any Alex reports this morning because I got into my car and had a flat tire. So today's been kind of crazy, so I'm not as prepared. It's already been a day. Yeah, it has been. Yeah, exactly. So we're kind of stretching out a little bit into next week. So we're working on the stuff today that will really be on next Wednesday's homework. This will be the last section, and then we'll do a review, and then we'll have a test. So already? Yeah, next week. Yeah. So. Just what? Respectfully. Yeah, that's right. So it's all right. It's gonna be on chapters 5 and 6. Atomic, orbitals and all of that stuff, electron configurations. So it should be all right. Yeah. So here's the topics that are due next Wednesday, 11/6. And so we're going to be taking what we know about electron configurations, and we're going to kind of look at some of the data behind that. So we're looking at ionization energies and properties in the periodic table. So I talked a little bit about the D block, right? It's on the 4s, and then the next energetic level is the 3D. So how do we know those relative energies of those different orbitals? That comes from the ionization energies. So we're going to be looking at ionization energies today, and we're going to get a little bit more information on the sizes of atoms. So some of the questions are related to atomic size and on the which one is more difficult to ionize and so on. So let's jump in. So we can look at these valence electrons in these orbitals, and we can decide, okay, what orbital is the electron coming from? It's coming from that outermost orbital. So in Alex, it's saying for each atom in the table below, write down the subshell from which an electron would have to be removed to make a +1 cation, and then into which an electron would have to be added to make the -1 anion. So this is pretty simple. The H atom, if we were to make a cation, we'd be pulling an electron from a 1s. And if we were adding an electron, find H up there on the periodic table, it has still another slot in the 1s. So it can go up to 1s2. It's 1s1. If we were to make an anion, that extra electron would go into the 1s as well. Okay. Let's not do zinc yet. I know it's the second one on my slide, but let's do argon first. Okay. So if we were to remove an electron from argon, what is that last subshell that we're filling on the argon row? If you need to think it through, we could do the electron configuration. So argon is 1s2, 2s2, 2p6, 3s2, and 3p6. So those last electrons, the last 6 electrons went into the 3p. So if we're going to make a cation out of argon, that last electron would come out of the 3p. So the answer for this one would be the 3p. Now that's not the answer for if we make an anion, because if we're going to put another electron on the argon, we've got to go around to the next row. It'll be the 4s. So the 3p's filled for argon, and so if we're going to make an anion out of it, it would be a 4s. And that's why argon doesn't want to be an anion, because if put it in the 4s, you could make an argon -1, but it would be looking for somebody to give that electron to. So it would be a huge reducing agent. It would want to give an electron to somebody. And so argon, you could make it, but it'd be really reactive, and it's not going to stick around very much. It's not going to be common. So it's going to find it. The first thing it bumps into is going to give that electron to it. Okay, okay, let's do the fluorine. So here we are. Fluorine is on the second row. So we're over there on the 2p block. So it would come out of a 2p orbital. And then if we were to put an electron on the fluorine, we have one more slot for the electron in the 2p. So it would go into the 2p. So over here, this would be, again, that would be going into we pull an electron out of the 2p, and it would be a 2p 4, right? That would be the cation. And then if we put it into the 2p, it would be the 2p6. We'd have all 6 electrons in there, and that would be the anion. Now zinc, look where zinc is in the periodic table. Okay, it's got that nice filled 3D shell. Oh, before we do that, let's look at how stable this anion is for fluorine. So F minus is isoelectronic. I want to keep using that vocabulary word so you guys are comfortable with it. Iso means same. So it has the same electron cloud as what? Yeah, the noble gas right next to it. Isoelectronic with neon. Okay. So it's almost, I'm trying to describe to you guys how stable the electron cloud is when you get 8 electrons in it. Those noble gases all have 8 valence electrons. And I'm trying to, it's almost like a musical chord. You know, you've got different notes. Every different electron has a different little frequency and so on. But when you get all of the notes in a chord, it just matches beautifully. You know, and that electron shell, when you get that 8th electron in it, it's just super stable. And so it's really hard. Once the fluorine makes a fluoride, it's super stable. It doesn't want to take on another electron, doesn't want to give that electron up. You make argon anion, it hates that extra electron. It's in the 4s. It's ready to get rid of it. Argon by itself has got 8 electrons in the outer shell. It's super stable. All those electron wave functions are just perfectly in tune with each other. Same thing with fluoride minus or oxide 2 minus. Or zinc when you have the 3D10. So let's look at this. If we were to remove an electron from zinc, that 3D10 is such a wonderful pattern of having all 10 electrons in that D subshell that you actually take an electron from the 4s. So for these for these transition metals, when you're going to ionize them, it's easier to break the s orbital than the d orbitals. So we pull that electron out of the s orbital. Okay, for the zinc.
And does that go for like iron and all of the metals in general?
I think so.
Or,
yeah, I think that first cation comes out, the first electron comes out of the s orbital.
Or is it just would it just be the ones because it's next to copper, silver, or gold? Because those have 10 as well, and it's a
so copper, silver, and gold for sure. They've stolen one of the s electrons already. So they're 3D, 4D, and 5D 10s, and 4s1, 5s1, 6s1. And so then when you're making a cation out of silver, you're losing that s electron. So you're pulling out the 5s electron. So it still has the 4D10. So that D10 is just super stable. And the only way I can think of it is that it's the resonance of all those waves. They're just perfectly in tune with each other. And to break that, when I say they're in tune, they've dropped further down in energy. So to pull that electron out, you're pulling it out of a deeper well. Okay. And then we get to which one would we add to? So the zinc, we've got a 3D10, it's full. The 4s2 is full. And so we're going to go into the P block. And the S and P block are all 4s on that row. So it's 4, S1 and 2, potassium, calcium. Then it drops to 3 as you go through the D block. And then it goes back up to 4. So gallium would be the 4P. So we go into the 4P. It looks like a 9. Let me change it. Okay. So that's just a little bit about when you're putting electrons on or taking them off and understanding the electron configurations.
So then for like silver or gold, would you go to the 4s if you're making an anion?
Mm-hmm. Good question. So let's just do this for silver and gold. So silver, Ag. So the electron removed would be coming out of the 5s. Okay. because we have for silver the 4d10. Okay, and then if we're going to add an electron, we have a slot in the 5s for silver, because silver would be 4d9, but it's already stolen an s electron to make it 4d10, and so there's an open seat in the 5s orbital. So we would add an electron to the 5s. Those situations are the clearest, okay, because we're real close to that D10. The iron and those in the middle are less clear. So I'm not sure that Alex is going to give you one of those in the middle, but the trend for sure is that the D block elements lose those s electrons when they're ionized. Okay, let's look at some of the evidence of these ionization energies. So notice that this energy difference, this ionization energy is an energy difference between the cation and the neutral. Okay, and so there's a nice little F block. And so everything is Aufbau, he says to Simba, and he says, "What is that shadowy place over there?" And he says, "That's the F block. You should never go there." So we won't talk about those. In fact, it is shadowy here. We don't even have all the F block data. Okay. Now, why wouldn't we have the F block data? Well, it's radioactive. So you isolate your sample, you start trying to measure the ionization energy, and the nucleus decays and turns into a different element. And so you're like, wait, I wanted to measure berkelium, and now I'm measuring americium. And the elements keep changing places on the periodic table. If that blows your mind, that's nuclear chemistry. So when a nucleus spits out an alpha particle, it loses 2 protons. And so that nucleus now moves to the left 2 slots. So things hop around on the periodic table when they're radioactive. So that's kind of crazy. But anyway, let's look at this. So there's some trends, and these are periodic trends in the periodic table, but the data is here in this first ionization energy. So here's all your trends. Trend 1 is that the ionization energy decreases with the size of the atom. That makes sense. If I've got a sodium atom that's as big as Texas, it's easy to remove that outer electron. If I've got a hydrogen atom that's as big as Walker County plus a few other counties, it'd be harder to remove that electron. Because what's holding the electrons together? It's that positive nucleus. So the further you are from the nucleus, the less force it takes to pull you off. Okay. Trend number 2. Across a row, so like if we go from sodium over to argon, it gets harder to ionize. Because as we're working our way across, we're adding more protons to the nucleus, so it's holding all of the electrons tighter. Trend number 3, the first ionization energy is unusually high from a fully filled subshell. That's what I was talking about, the electron cloud sort of relaxing in energy when it's filled, when it's a P6 or an S2 or a D10 or an F14. When you fully fill one of those subshells, the waves of the electrons are resonant with each other, and it makes the whole atom more stable. So it's hard to ionize. It's hard to pull one of those electrons out and to break that stabilization. The half-filled subshells are also somewhat stable. Not super stable, but they're unusually stable. We'll see that in the data. And then lastly, the trend number 5, if you go past a fully filled subshell or past a half-filled subshell, it's easy to ionize. So that's just because the cation has the nice little resonant structure. So let's look at the data. It's all right here. So trend number 1, the ionization energy decreases with the size of the atom, and we can see that. So as the atoms get larger, like towards radon, it's really hard to ionize helium, really easy to ionize radon and mercury. So as the atom gets larger, it's easier to ionize. You don't see a lot of that change, but it's a little bit. Lithium, it does kind of trend down in the alkali metals, but you really see this effect in the noble gases. And what we're looking at is the difference between, say, this really stable helium 1s2 and the cation 1s1. And so these energy levels are closer together right here because the atom is so much larger. So this is your general trend. I think you see this in the notes. we've got the periodic table there, and just draw a diagonal arrow showing that helium is the hardest to ionize and francium is the easiest to ionize. And so if something is on the periodic table, if something is to the right, then it should be harder to ionize than something to the left. So going across the row, these are the rows in the periodic table. Helium, hydrogen to helium, lithium to neon. You see that? So that's the second row right there. Then the third row, sodium to argon. So as we go across the row in the periodic table, it gets harder and harder to ionize that atom. Then we have the D block. So this is row number 4 with the 3D elements in the middle. And then row number 5 with the 4D elements, and row number 6 with the 5Ds and the 4Fs. So we have the F block, at least the actinides, and then this is what we're seeing. It's very easy to ionize the lithium and very hard to ionize neon. Again, this is that fully filled subshell, super stable. And so this, why does this happen? Well, every time we march to the right on the periodic table, we're adding more protons and we're adding more electrons. But if I come in as an electron, I'm into an orbital, but some of the electrons that have been added prior to me getting there are going this way, and I have an independent view of the nucleus. So I'm really drawn in. It's not like I just see the extra proton that was added when I came along. I see all the other protons, that those other electrons are not in my way. So as we add more protons and add more electrons, inadequate shielding of the nucleus allows all of the electrons to feel more attraction. So every electron in the atom is feeling the attraction to the added proton. So all of the atoms shrink up as you go to the right in the periodic table, and it gets harder and harder to analyze or ionize. And you can see the steepness of these arrows is really telling you the effect. So so look at the steepness of this arrow right here. That's showing you the effect of adding more protons and all of the electrons being attracted to that nucleus. You know, the size effect was pretty gradual. The size effect was just right here, going from helium to radon. The slope of that decrease was pretty small. But look at the slope of this increase from lithium to neon. That is huge. Okay. So we're adding protons and electrons, and all the electrons are attracted to that new proton. So it's the same trend. As we go across the row, we see an increase in the ionization energy. So this allows us to predict the relative ionization energy of the elements. So let's find our elements here. So this is potassium here, cesium is here, sodium is here, and magnesium is here. So magnesium is to the right of sodium, then you have potassium, then you have cesium. So we want the easiest to ionize to be 1. So which of these is going to be the easiest to ionize? So this is the hardest, and this is the easiest down here. So cesium is down in that corner, so it's going to be ionized first, or the easiest. So we'd be 1 there. And then going up, we see potassium. Right? Do you see that? So potassium would be second. And then this says that sodium is easier to ionize than magnesium. So does everybody follow the logic there? We're just kind of using that trend. And so it gets harder to ionize going up, so that's why it's cesium, potassium, sodium, and it gets harder to ionize going to the right. And so then that would be sodium and then magnesium. We try not in these problems to give you things like sulfur and bromine, because those are diagonal to each other, right? So that's the one situation where you're like, gee, I don't know. The sulfur's above bromine, but it's also to the left of bromine. And so that's a situation that's difficult. So hopefully Alex doesn't do that to you. Okay, so that's using this trend in ionization potential in the periodic table. So let's look at some of these other things about the subshells. So this says that the first ionization energy is unusually high from a fully filled subshell. So can we find the fully filled subshell data on this chart? Where do we see that? Well, we certainly see that in the noble gases, right? All of those noble gases have something P6, right? NP6, whether N is 2 or 3 or 4, it's always a P6 for that noble gas. So that's a fully filled P subshell. We also have beryllium, magnesium, at least beryllium and magnesium. See over here on the periodic table, beryllium and magnesium are the S2s, and so they're fully filled S subshells. And then we have the D subshells fully filled. So zinc and cadmium in particular have fully filled D subshells. So that's a 3D10 and a 4D10. And this is just showing that those are unusually high. Like this trend right here is not a perfect line. Look at the beryllium. It's above boron. So from beryllium to boron, that kind of breaks the trend. Boron's to the right of beryllium, but beryllium is a fully filled subshell. Okay, it's also unusually high from a half-filled subshell. So where are the half-filled subshells in the periodic table? N and P and AS, so nitrogen, phosphorus, and arsenic, are P3s. So it's a 2p3, and you can put 6 electrons in the orbital. So the 2p3s are half-filled. Each electron has its independent view of the nucleus because it's in 3 different p orbitals. And so that's also a nice resonant pattern for the atom, and it has a stable electron cloud. So there's nitrogen and there's phosphorus. And there's arsenic. And again, the trend is not so strong as you go down the periodic table, but for nitrogen and oxygen, it's a pretty big difference. And then the ionization energy is really low or unusually low when you're one past the fully filled subshell. So when you go past the P6s and you get past the noble gases, you're in the alkali metals. And so those are all S1s. And so those are real easy to ionize. Also the P1s, like aluminum. So aluminum and boron, those are easier to ionize than you would expect. And then gallium too, and indium. Okay. So you've just passed a fully filled subshell, which means that if you were to take that extra electron off, the cation would have the fully filled subshell. So this means that the cation has a stable electron configuration. So these are just the trends in the ionization energy data. So this is what we've done with the atoms. We've taken them and we've analyzed their data and seen how hard and tightly they hold on to their electrons. This gives us insight into their chemistry. So that's why we're talking about this. This valence electrons and the 2p6 and the 2p3s and all of that figures into the chemistry. So y'all are learning this foundational part of how the valence electrons are stable in their configurations. So then the first ionization electron comes from that s orbital for the D and F block elements. And so if you're in a D block, say you're here in nickel or something like that, and you want to make a nickel cation, it's going to pull that electron from here, from that 4s2. Okay. And that happens here in these D blocks. And also the F blocks. So now we get to the Alex problems. I like these problems because this is using the data that you would get from the lab. So you're going in here and you're looking at the ionization data. Now we have some other ionization energies. So IE1 is the ionization energy for the first electron to come off. Okay, so this went from the neutral. Let's say, let's just call it A for an atom, okay? So you have A, and it's going to A plus, and here it's going to A2 plus, and this is going to A3 plus, and A4 plus, and A5 plus. Okay, so that's what's being shown by this little bar chart. And this is the amount of energy that it takes to get from A to A2 plus or A to A3 plus. Okay, and notice it's really low for the first one. And this is saying that we're in period 4. So we can look at the 4th row of the periodic table and we can try to figure out which one of these elements would have this kind of pattern. So it's saying it's real easy to make a +1 cation, but really hard to make all these other cations. So it's probably potassium, because it would be real easy to remove that 4s electron from potassium. And then to go to potassium 2 plus, potassium cation would have the same electron cloud as argon. So K plus looks like argon. It'd be really hard to break that electron cloud. So you can do it, but it would be this much energy. So what you're looking for in these problems with Alex, you've got a low energy and then high energy. And so the low energy ionization is really a count of the valence electrons. So let's do another one. So here we are, first 5 ionization energies of a period 2 element. So period 2, we go to the periodic table and we're looking at period 2. And we've got 3 low energy electrons. So what element do you think it is? What did I say on the last screen? Let's go back. The low energy values is a count of the valence electrons. And so if we go on period 2, and we're looking at this and we see 3 low energy ionizations, then that's a count of 3 valence electrons. So it's looking like boron, right? You see that? Boron is in group 3A right here. And so we're taking boron and we're making here B plus, and then we hit it again and we make B2 plus, and we hit it again and we make B3 plus. And B3 plus, if you look at it, if we remove 3 electrons from boron, it looks like helium. So that's isoelectronic with helium. That is the helium core. And so then when we try to pull that 4th electron off of boron to make B4 plus, we're trying to break a noble gas fully filled electron shell. And so that's going to be really tough. You can do it, but it's high energy. Okay. Let's look now at the sizes of atoms. We've kind of taken, this is some of the data that I used to calculate that Texas picture for sodium and so on. So going from hydrogen to sodium was this jump right there. One way they do this is with the diatomics. Like they take the molecule's bond length and they divide it by 2 and they can get the size of the atom. Okay. Because again, it's really difficult to think about the electron cloud. It just kind of fades away. So there's really no hard surface. So how do you know what a size of an element is? Okay. You have to like take the bond and then take half of that bond length and you say, well, it'd be like if these atoms were bumped against each other and stuck, half of that distance of the bond length would be the size of the atom. And so this is what they did. So that's the way they get started on the data, and then they could react molecules with other molecules and look at the changes on their bond lengths, and they could get the whole table And that's what they've done. They built the whole table of sizes looking at diatomic molecule bond lengths. So what is the trend you see? Well, this is the largest down here, and this is the smallest up here. And it's a pretty smooth transition as you go. So you could draw this big arrow like that and do size. So it goes the opposite direction as the ionization energy, right? And that makes sense that it's hardest to ionize the smallest atom and easiest to ionize the biggest atom. So the arrow, you draw the same diagonal arrow, and if the head is pointing towards helium, that's ionization energy, and if it's down here pointed towards francium, that's the size of the atom. They go in opposite directions. So here's a picture of those plotted on the same chart here, and you can kind of see that lithium to sodium, potassium, it's not quite linear. It does sort of taper off in size. And you can see here helium, the noble gases going up. But look at that big jump when you go to the next one. So you've got the fully filled subshell of helium, and then you put in the 2s. You have a huge jump in size. I mean, 3 times jump in size. Then you get to neon, and then you go to sodium, and you get a huge jump in size. So as you add those shells, they get bigger and bigger and bigger. Okay. And then you can see that the size decreases dramatically as you go across the row of the periodic table. So going from sodium to argon, we're adding those extra protons and adding the electrons, and the shell gets sucked in tighter and tighter until it's really small, like an argon. Okay. Now, what if we make cations? If we take electrons off of the atom, look what happens. We go from like almost cut in half, going from aluminum to aluminum 3+. So we pulled 3 electrons off, and that atom is now shrunk down to an ion size that's really tiny. So cations are really small. If we put extra electrons on, the electrons repel each other, and so then they expand. So anions are big. You see, this doesn't quite double, but it's 70% higher. And so then we have problems like this in Alex asking us to rank the different sizes of the cations, anions, and elements. Okay. So here's an example. So it says rank the sizes of the ions and atoms. So here we have a bromine, a krypton, and a bromine ion. So we can circle those here. Here's krypton, here's bromine. So krypton's the smallest, and we want it in decreasing size. So we want the largest first. So bromine's bigger than krypton, and then bromide, Br minus, is bigger than bromine. So this should be Br minus, and then Br, and then Kr. Does everybody agree with that? You see increasing size going to the left. So bromine's bigger than krypton. Okay, let's do these different halogens. Oops. So now we have chlorine, bromine, and fluorine. So they're all right here. So decreasing size. So the largest one is bromine, then chlorine, then fluorine. And now we've got a cation involved. So we got magnesium, magnesium cation, and sodium. So we've got this right here. So the cation is going to be smaller than the neutral. So the magnesium cation is going to be the smallest thing. And this is telling us that sodium is larger than magnesium. So we start with sodium. And then we have magnesium neutral. And then when you take an electron off, it gets even smaller. So we have magnesium cation. Okay, that should make sense to you using this little trend chart. Okay, let's do some more. Okay, now we're ranking atomic ionization energies. So here we have francium and tellurium. So I'm circling them on the periodic table here, and oxygen. Okay, so it's right up here. And we know that it increases to the top right side of the periodic table. So this is telling me that you want 1s next to the least energy and up to 3 next to the highest energy. So the oxygen would be the third one in this. So that'd be 3. And then tellurium is way far to the right of francium. So francium would be 1 and tellurium would be 2. Does everybody agree with that ranking looking at the diagram, right? So the hardest to ionize would be oxygen, the easiest to ionize would be francium, and then tellurium would be in between. Okay. Let's do another one. Cesium, helium, and potassium. So here's potassium, here's cesium, and here's helium. We know helium is the hardest thing to ionize, and so we're going to go ahead and put that at 3. And cesium is way down here in the bottom corner, so that's going to be 1. And so potassium will be between those two. We can kind of see that here. So here's helium. Where's cesium? Here's cesium. And then here's potassium. It's not much higher than cesium, but it should be higher. Okay, now for something different. Again, as I was making these modules, I go through and I say, yeah, that's something I want to teach them. Teach them all about electron orbitals, teach them about the electron configurations, ionization trends, and periodic table. In this same chapter are some other trends, periodic trends, and this one ties back to some of the acid-base reactions we did. So it's a totally different topic, but as I'm selecting the modules out of this chapter, I saw this topic, and I was like, yeah, I want to teach them about anhydrides and whether they make basic or acidic solutions. So this is a totally different topic, but it's one set of problems in here on Alex. So if you get there and you're like, is this even in the right chapter? It is. It's in this chapter of atomic periodic trends. And so if we remove water from some bases, we get metal oxides. So if you have like potassium hydroxide and you remove water, you need 2 molecules of that. You remove water, you get potassium oxide. So this is what you get if you really dry it out. And this is the way you find some of these minerals in nature. So a lot of times in nature you find the anhydrides because the geologic heat and so on has driven water out of the mineral. So here we have 2 potassium hydroxides. If we really dry that out, then we're able to get the potassium oxide, K2O. If we run this in reverse, then it can give basic solutions. And so if we take something like potassium oxide, what happens when you burn stuff? You get ash, right? You've heard of that? You get ash. What if you burn potassium and you make potassium oxide? It's burnt potassium. It's potash. So you've heard of potash, potassium ash. This is what you get. You get this solid substance, potassium oxide. If you put that in water, you get a basic solution. So it's essentially running this reaction in reverse. We're adding water to that structure and forming hydroxides with the potassium. So if we remove water from some acids, we get nonmetal oxides. So if we take sulfuric acid and dehydrate that and we pull the water out, it's not easy to do, but if we were to do that, we would get gaseous SO3. Okay. What if we burn sulfur in, say, we're power plants? So we're burning coal, and coal is a mineral we dig out of the ground. It's got other substances in it. Sometimes it has sulfur in it. And so if it's got sulfur in the coal, we're making CO2 with the coal because it's carbon. We make SO3 with the sulfur, and it's a gas, and it comes out of the stack. What does it do when it gets out of the stack? It floats around in the atmosphere, and what else is in the sky? Clouds. And so the SO3 mixes in with the rainwater and you run this reaction in reverse and you make sulfuric acid in the clouds. So this is acid rain. So if you run this reaction in reverse, SO3 gas, the sulfur oxides, and they mix with water in the atmosphere, you're making sulfuric acid in the clouds. And then it falls down on the ground. And it can dissolve calcium substances like all of our statuary and our buildings and our concrete. It can change the pH of our rivers and lakes, and we can see some environmental effects. And so when you hear about acid rain, that's what's going on here. It's the non-metallic oxides will form acidic solutions. The metallic oxides will give basic solutions. So that's a periodic trend I'd like for you to know. And there's some Alex problems associated with that. So let's look at some of them. So Alex will be asking you for these blue reactions, but I wanted to describe it using that term anhydride. So anhydride, hydride is water, right? So we're removing water. So we're taking away that water reaction. So here we are with this set of reactions. So here we have a sodium oxide with water, and that's going to make the 2 sodium hydroxides, okay? And when I see that sodium hydroxide, if I make an aqueous solution out of that, okay, that's going to be a basic solution. So that's what I would write in Alex. I'd write in the 2 NaOH. Now, I'm not sure, you need to check. It might require you to do this, Na plus 2 OH minus. So again, check on Alex what it wants you to do, but it ought to accept both of those answers. Then we have the potash, the K2O reacting with water. You're going to make 2 potassium hydroxides. We see that hydroxide, we know that's going to make a basic solution, something with a really high pH. And then the acid rain reaction, we have SO3s going into the clouds and reacting with water. We're going to end up with sulfuric acid, and that's going to be an acidic solution. So we recognize H2SO4 as sulfuric acid, and it's right there in the name. It's an acidic solution. What if we did let's do NO2. So some of the nitrogen in reactions and even automobiles, the nitrogen gets into that cylinder. It's 80% of our atmosphere. So we're burning gas with oxygen, and the nitrogen is in there, and sometimes it reacts with the oxygen. So we might make NO2 plus H2O. Okay. And that's going to make HNO3. Okay. We're going to have an extra hydrogen, but anyway, this is what's going on with the nitrogen. It's going to make nitric acid. So those are the acid-base properties of these oxides in water. And that's that last topic on next Wednesday's homework. So for next week, we've got, a Monday assignment, which we've already covered. We're pretty far ahead, so you may want to check the videos, because can you remember what we did 2 days ago? Probably not. I can't even, So you want to go back when you're working on the Monday homework over this weekend, go back and find that video, and then you can sort of check yourself on that. And then this video is really for next Wednesdays. But here's the deal. You're now really prepared to start doing that knowledge check for next week. Once you're finished with the Wednesday homework, if you do it early, then you can start on that knowledge check, which should serve as a review. Now, I had a request from one of the students to put up another extra practice. And so what I'll do is I'll go find an old exam too, and I'll put that on Blackboard. And then you'll be able to just sort of practice with some of the multiple choice type questions that I asked in the past. And that'll help further prepare you so that you have a good chance of raising your score on this next exam. Does that sound good to everybody? All right, great. So y'all have a good weekend. All right.